Recording is on.
Okay, everybody. So this week we are going to continue the discussion of finding common ancestor. So last week we discussed about finding common ancestor using parent node link. So navigating from child node to the parent node and finding the common ancestor. So there is another version of this solution where without using parent nodes. So here Karina is going to discuss her thought process. Yeah, go ahead, Karan. Go ahead, Karanya. So, how are you going to find out common ancestor?
Let's take an example. This is the tree A, B, C, D, E, F, G, H,
Yeah,
and we have to find the ancestor, common ancestor for E and H.
E and H. Okay,
Yeah.
okay.
So the common ancestor for E and H is nobody but A, the root parent.
A is the only one. Yeah,
A is the only one. So if we want to find the common ancestor for example, D and E, my thought process is we do have no tracking of the parent value here. Each node has its value and the left and the right.
uh-huh.
So we have to start from the root
Yeah,
node. So
yes.
we compare the root node with two values, whether D and E. They are not equal. So we will traverse through the left of the root node,
D and E not equal. I did not understand what is that. D and E not.
whether A is equal to D and A is equal to E. So
But
the obviously,
D is not our input, right? Input is E and H.
for example, we can take D and E, which has the
Okay,
common parent.
okay. You are taking another example.
Yeah, another example.
Common ancestor for D and E.
Yeah,
Okay.
D and E.
Hmm.
So we are going to search the entire left side. In that case, if I go for B, B is not equal to D. So
Even this first condition also false, right? A equal to D and A
yeah,
equal to E. It's
it
never
is.
it's false.
So we can't return the root. Okay. So what shall we do here, Suresh? How
So
can
what
we
is
compare?
so A equal to D? What is that condition?
We are comparing the root with the two nodes which we have got.
Yeah, we there is no need to compare the values of the root, right? Our intention is to find out A never be equal to D, right?
Okay.
Unless you compare A dot data equal to D dot data, okay, there might be possibility that the data you putting at A and the data you putting at D
B.
might be equal.
Okay.
Yeah, but our intention is to find the common ancestor, right?
Okay.
So
So
in it, yeah,
yeah.
go ahead. Yeah, try it out. So if you want
Uh,
to,
Now I'm going to focus on the left and right,
uh-huh.
where I'm going to compare the B dot data with D dot data and C dot data with everything, with
Mm-hmm.
these two values, where they
Yeah,
are not equal. So I'm going to continue with the left side,
yeah,
and left side B dot left and B dot right, with where B dot left and B dot right is equal to these two values.
yeah,
So I'll end up with B.
yeah. So
So this is
basically,
an easy method. But
exactly.
what if I have a tree like this actually? Yeah, then now I have to find the ancestor for E and H.
Mm-hmm.
So there, I don't know how I will solve the process
Yeah,
for E and H.
E and H.
I
Yeah.
have to
So
submit with the result A.
A, right? Yeah.
Hmm.
So previously, let's come back to the previous question, D and E, right?
Yeah, D and E.
For D and E, so why did you go with the left side only? Because D and E are on the left subtree,
Yeah.
correct? When you started with A, so what are we doing in reality? What are we doing is when you started with A, we are seeing is D on the left subtree of A.
Okay.
E is on the left subtree of A.
Okay.
That means yeah, E is D
On the
on
left.
the left subtree.
Okay.
Okay, left subtree of A.
Okay.
So is it true or false? What is the
Okay.
result? We got it. We got result equal to
True.
true, right? Put true
Yeah.
there. Yeah. Now is E on the left subtree of root?
Right. Oh, sorry. On the
No,
left.
not left. Only left. Only left. Okay. Because we will check whether both nodes are on the left side. Left subtree of root
Okay, which
equal
is true.
equal to, let's say this is true, right?
Yeah.
Now now what it is telling is, what it is telling, that the fact is the nodes are unique. We are the given the input already unique, so you never be able to find D or E on the right subtree because they are already found on the left subtree, correct?
Yeah.
So
So, okay.
so if both are true, what it is saying is, it is safe to navigate to the left side because
Okay.
both found on the left side, correct?
Okay.
So if both are true, then the same algorithm, the same finding algorithm. Basically, what you did on the step number one is you started at A and you find all the way. Is D in anywhere? Did you find D anywhere? In step number two, you started at A and you navigated all the left side and find E. Did you find E anywhere? So you did a two searching process. Basically, you searched for D on the left side, you
Mm.
search it for E on the left side. Okay, that process can be again started with B because basically you navigate to the B basically. So now root becomes B. Okay,
Yeah.
now you do the same process. Is now root equal to B. Okay,
Mm.
step number, yeah, it's kind of step number three, but it's basically same step number one and
Same
two you
step.
are
Yeah,
making.
recursively we are doing it.
Exactly. Recursively we have to do. So now root equal to B.
Oh, yeah.
Now root equal to B. Now step number one. Is D on the left subtree of B?
Is B. Yeah.
Yeah. No, no, no. Is D. Hey Arvind.
Aravind is
Hey Arvind, how are you doing? You just joined. We can't hear you. Are you muted?
Yeah, yeah,
Hey Arvind, doing good? How are you doing? Um,
yeah. I'm doing good. Thank you for asking.
Nice. So did you get a chance to look at the last week problem? We are discussing the common ancestor problem.
Uh, Actually, I didn't get through the didn't
Okay.
go through the video, but I know the problem of
Oh, nice.
finding.
You already
Yeah,
know the problem. Okay. Have you
yeah.
practiced and solved it before?
Yes, actually, I went through these concepts a bit earlier, like a
Very
little
good.
earlier, around
Very good. Very good.
around a
Very
month
good.
ago.
Very good. So, did you solve by using parent node links? Because there are different ways of doing it, right?
Yeah. Okay, so I'm not sure what approach was discussed here in the last session, but
In the last session, we discussed about the by using parent node. Let's say you gave the two nodes, and we will start by navigating up from the both nodes. We'll navigate up until we find the common node. That's one.
That's the approach I know of. Yeah.
Nice, nice. So you already know that approach. So now we are discussing about
Hmm.
the finding the element without knowing the parent nodes. We don't have a, let's say the given algorithm is you have a tree. You start from root, but we don't have a. I will give you two nodes. You don't have the parent node link, so you cannot use the parent node link. That is the algorithm we are finding. Okay?
Okay, so we are just given two nodes
Two
that
nodes
exist
and
in
root
the
node
tree.
and root node. Yeah. Hey Vanilla.
Hi, Suresh.
Okay,
Sorry, I just joined.
root node. Okay.
No problem, no problem. Yeah, go ahead, Arvind. Yeah, we'll have access to the root as usual. Every time if you are giving a tree, you have access to the root, and also we are giving two nodes in the tree. Okay. Now we are going to
Yeah,
find the
yeah.
common
Okay.
ancestor. Okay. So Vinila, so we are discussing about the common ancestor problem. So did you get a chance to look at the problem in the past anytime?
Sorry, Suresh. No, I didn't get that. I didn't saw that problem.
That's good. That's no problem. We will explain. So basically, the common ancestor problem is very popular problem in interviews. So Karanya is going to explain. I will let Karanya to explain what is the problem, and then we'll explain different methods. Yeah, go ahead, Karanya. So what
Yeah.
is this? What is this common ancestor problem? You
Yeah.
don't need to erase the everything. You don't need to erase. Just explain. Yeah.
Uh, the common ancestor problem is that we'll be given two nodes. We have to find the common ancestor for the two nodes. For example, here we have a tree, a binary tree, where um, we can take D and E, the child node, the leaf node, D and E. The common ancestor for D and E is also B. Sorry, it's also A and B. But the first common ancestor we have to find, which is B. So the first common ancestor for D and E should be B. So last week we have seen the first approach of the first common ancestor, where we are maintaining the level. Sorry, we are not maintaining a level. We are maintaining a parent node, keep tracking of the parent node of each node to find the common ancestor. Uh, to simplify that, let me explain the process which we have discussed last week. Um, okay. So as you can see, A, B, C, D, E, let it be F. Okay. B, C, D, F. Okay. Now, which H. So now here, let it find the first common ancestor for H and G. So we already had a we already seen about maintaining a parent node with each node. For example, for a node, we will have its value. We will have left and right node of that node, and we will also maintaining a value of the parent node of a node. For root, it is -1. For H, it is F. For G, it is B. For D, it is C. E, it is C. And for C, it is A. So, to simplify the problem, for H and G, we had a track like this. We discussed about the node and how we are going to reach the two nodes. So for for H and G, for H we have F in the first iteration, iteration 1. For G we have B, the iteration 1. In iteration 2 we'll end up with F will have B and B will have A.
Yeah.
In iteration 3, B will have A and A will have no one. It has a parent null.
Null. Yeah.
So the problem is we are approaching it in a right way, but the thing is we are starting with different levels. You can see H is in its different level, and G is in its different level. So this is level 1, level 2, level 3, and level 4. To overcome this problem, we just want to start in the same level.
Yes. Then we can find the common ancestor. Yeah.
Start in the same level and
See
find
where
the
they meet.
common ancestor.
Basically, we'll start at the same level and see where they meet, right? Where
Yeah.
both the paths will meet.
So
Yeah.
for that, we'll compare their levels. Which one is higher? We'll jump to their parent, to F, and from F we'll go for F it is B, and for G it is B. Then we'll come up with B as a solution. First common ancestor of H and G is B. This is the solution we discussed last week,
Yeah.
and now this week we are going to see, without having the track of their parent node, how we can find the first common ancestor of two nodes which is given.
Yeah.
So this is something like the common parent of both the elements, right?
Yeah,
You can say.
Exactly. Common parent. Basically, it's not direct parent, but ancestor. That ancestor means parent's parent. It's kind of,
Yes.
yeah. That's what ancestor means, right?
Yes.
So, given two relatives, you and someone in your big family, we will see where they meet, right? Like, your father's father name, kind of. You will find out, hey, that is the grandparent or ancestor of both the families, right?
Yep.
From there, everybody common. From B, both the B and A are common. So, but we need to see first common ancestor where they meet those two nodes, right?
Yes.
So, this is they are good, a good explanation, Karina. Very good. So, with this, it's easy to find. Right? Let me give you few questions before going. So, let's say, what is the common ancestor for H and E? I'm asking Vinila or Arvind. H
Yeah.
and E. H and E
Yeah,
in this
A.
example.
Yeah.
Yes, yeah, because if you go back from H to top, they are not meeting until A, right? H is on the left side and E is on the right side, right? Vinila, is it clear?
Yes. Yes.
Because they will only meet, if you go up, they will only meet at the level A. So now another question. What is first common ancestor for D and C?
D and C. It's A.
D
Yeah,
and
it will
C.
be C.
It will be C, because why E will come into picture. E is just a sibling of D.
Okay.
You don't even go to E, right? So we are asking about D and C, right? So it's kind of you don't. This is the only thing which you cannot relate to the real life example. So let's say D is a child of C, right? In this situation, D is a child of C, right?
Yeah.
So you can think of in the chain of relationship, they meet at the same place. Like C is the parent, and C is on the path to the parent. So C itself is a common ancestor for C and for D as well. So you can think of as two paths, all the way from D to root. Basically, the given node, from the given node to the root. What is the path for D? It's a DCA, right?
Yep.
The path from C to A is C and A. So both will meet at the C, right?
Okay.
So
Yeah.
that's basically, yeah. So basically, the common ancestor for in this example is just C only, because that's where both will meet. If you navigate from D, you'll navigate and see whether you are finding a common. So C itself is a common. Yeah.
So in this case, for example, if common ancestor for D and A will
D
be
and A. Okay. What is the answer? D and A.
A. Is it
A
A
itself.
or
Exactly. A itself, because yeah, A is the answer, because both paths will meet at A.
okay?
right? So, but in order to find that, in order to find it, so here what Karnya said is both are at the different level. The example, the first example is H and G, right? H is at the level 4 and G is at the level 3, right? If you start navigating at the both the same time, if you started both time, what happened here in the table, you never be able to see both the nodes B and B. But that's why we are seeing what is the longest path, and we will jump that many times. The delta, basically we'll find delta. So level 4 minus 3, yeah, 4 minus 3 equal to 1, right? There is a one level difference between H and G. So we will equate that level. So that means that delta is one level, so we will jump that many times, and then we will start both at the same time. So we discussed about similar problem like intersecting linked list. There are two linked lists. We need to find intersecting node. I don't know whether you remember. I don't know whether you guys joined or not. So we discussed, and while we are discussing about linked list, we discussed about that problem. So similar problem here. Basically, we will find what is the longest path, and then we will jump to that level. We will make sure we are at the same level, and then we will start navigating to the top. Okay. Are you opening that the linked list problem? Or? I think Karanya is trying to find that problem. Yeah, linked list. Determine if two linked lists, exactly, that is the one. Yeah, determine if two linked lists are intersect. Yeah, this yeah, that's the one. So yeah, if you go to the algorithm, run test case one. Yeah, scroll down. Yeah, see, step number 1 is, right, find the size and trial elements, and step number 2 is compare trial nodes, and then step number 3, find the longer and shorter lists, right? So similarly, we are doing the similar thing here. So find the longer path, and then advance the pointer. Step number 4 is advance the pointer in the longer list by the difference in the lengths. So we can think of as a linked list problem here. Similar problem here. From the nodes, we are trying to go to the root node, right? Root node is, you can think of as the end of the linked list. So now we are advancing the pointer to that difference. Now when you advance it here, you advance only one time. Now F and G are at the same level, and they are same distance from the last node, which is A, right? Now you can find where they're intersecting. They are intersecting at B, correct? So the same thing happen if I ask you between H and E, even H and E, right? H and the level of the length of E is 3, and length of H is 4, correct?
Yeah.
So 4 minus 3 is 1, and then we will navigate H to 1, just a delta, so it will go to the F1. Now we'll start F and E at the same time. We'll have 2 pointers, and F and E will meet only at the node A, right? That's where the common ancestor. So you guys understood the problem. They're using parent node, if you have a reference to the parent node, that's the way to solve the problem. Okay. Is it clear to both of you?
Yes.
Yes, Suresh.
Awesome. So now we are discussing about a different way of doing. You don't have a link to the parent. So if I give H and G, let's say the same problem. First, let's take the H and G. How do you find the common node? H and G common. Yeah, for H and G, what is the first common ancestor?
V.
B is the B. We need to find B is the answer, right? So how can we find without having parent node? What do you do? Any ideas? We need to get the answer B. Yeah, you can put equal to B. Yeah. So now Karunya has some ideas. Let Karunya to drive. So what is the Karunya? You unmute and speak about the idea we just discussed.
The approach is, since we are not for each node, here we are maintaining only the node value left and right. We are no more maintaining any parent value.
Yeah.
So the approach is to traverse from the root node throughout the tree throughout the tree in a level wise, or in any order traversal you want. The first
Mm,
step is,
yeah.
uh, if we want to find the first common ancestor for H and G, we'll look for the H and G in the left side of the root.
Yeah.
And is there H and G in the left side of the root? Yes, H and G is in the left side of the root. So we
Yes.
need not to go through the right side of the root. So we can traverse each and every level and find the common ancestor. That's how I begin with. So
Yeah.
Suresh was directing the steps.
Yeah. So basically, the steps is, so yeah. So what you need to do is, first we'll take the um, pointer pointer node equal to root. Okay,
Yeah,
node equal to root. You can put that. Yeah.
pointer node is
Yeah,
equal.
step number one, n equal to, let's say n, or node, anything is fine, equal to, you start from root. Okay, now find, like, step number two is, we need to find between h and d, right? See,
Yeah,
step number two is h on the left subtree of node, is h on the
left
left
side.
subtree of node. Okay. Uh, is it true or false? What is the value? I will ask you,
True.
Vinila and Arvind. Yeah,
Yeah, it's true.
true, right? Because H found on the left subtree. Next, step
Yeah.
number three is G on the left subtree of node. Node
True.
at this point, node equal to root. Yeah,
Yeah.
this is also true, right? Now, if you get these two's checking, if you get step number two and three both are true, what it is telling is both nodes are on the left subtree. Basically, one another input here is, whenever we get this problem, all the nodes are unique. That means you never see G or H on the right side. So all the nodes are unique, so there is no duplicates in the nodes. That is first input. So now you can safely ignore the right subtree, correct? Because you already found both the nodes on the left side of the tree. So that means you can ignore the right subtree. That means you need to process the same steps. You need to process the same steps using, now node becomes step number four. Step number four is basically node equal to node dot left.
Root
Node
dot.
dot left.
Okay, yeah.
Because you call node dot left, don't call root, because now what happens here is, now node becomes
B.
P.
B, right? Now go back to the step number two. It will kind of loop. Basically, you will loop it. Now, is H on the left subtree of B? Is left subtree of node? Basically, the same thing. Left subtree of node.
True.
Is it true or false?
True.
H is on the left subtree. True, right?
Yeah.
Yes.
Yeah. Now, step number six is basically same thing. Is G on the left subtree of node? Always left
True.
subtree of node. Node is right now pointing to B. True or false?
True.
False.
Who said true?
Yeah, me.
Yeah, how it is? Because you are looking G, and you are looking G on the left subtree of B. Left
Left
subtree of
subtree.
B is F and H.
Okay, okay.
So now you did not find G on the left subtree, right? G is
Yeah,
on the right subtree of B, correct?
yeah.
So since you're always checking on the left side, what happened here is these two steps you got different value. You got a different value. So that means H found on the left side, G found on the right side. What it is telling is that is the common ancestor, right? That's where the diverging, basically, that's where the actual nodes are diverging. So when you find something like this, then you simply return the value of the node. If you find one is true and the other one is false, then that means you found one node on the left subtree, you found another node on the other subtree. Correct?
So we need not to find it. Suresh.
We need to find the common ancestor, right? Our
That we
our
just want
intention
to
is
find the G on the right subtree. We just return the node which we are currently pointing to.
exactly, because that is a good point. You are telling really good point. Before even doing all these things, we need to make sure the given nodes are already in the tree, somewhere in the tree. That's right. So here we are always looking for G on the left side. We don't know whether G on the right side. But if you are doing the validation check before even starting this algorithm, make sure G is on the tree. And if you look at step number 3, you already found G actually. Step number 3, you found G on the left subtree of, if you start from root. Correct? G is definitely on the tree, right? So of course we get false on the step number 6, because you're looking for G on the left side of B.
Yeah,
That is the reason you got the false, but it is on the right side of the B.
tree.
So here at this point, both, you know H is on the left side and G is on the right side. That means B is the
Common
common
ancestor
ancestor.
system.
Correct?
Yeah. Okay.
So you can ask one more thing. There is one more possibility here. Can you guys tell me?
With the same root means.
This is the same root. Yeah, B is same root, and you found H on the left side, G on the right side. So that means uh, basically first check got true. Step number 2 and 3 you got true and true. Step number 5 and 6 you got true and false. What is the other possibility? Let's say
False
another
and true.
False and true.
false and true is also another possibility, but that is also same thing. That means if you get false and true, that means H is on the right side, G is on the left side, right? If you get the step number 5, if you get false, the what it is telling is H on the left side of node? No, that means H is on the right side. Is G on the left subtree? Yes. True means G is on the left side. So you got the reverse answer. Basically, H on the right side, G on the left side. That means you can return B. No problem. Right? What
Okay.
is the other possibility is, what is the
False.
other possibility?
Root itself one of the node. The root
Root itself
B.
is one of the node. What I'm asking here is
False,
there are
false.
false, exactly. So there are three different cases, right? Four possibilities. One is true and true. Other one is true, false, false, true. We already covered those two. Last option is false and false. You get false and false. Now let's say false and when do you get false and false is, let's say G has another left right node. Let's draw something. G has G on the tree.
B.
No, G. No,
I'm
on
just
the,
reading. Okay, on the tree itself, shall I write?
yeah, on the tree itself, let's say GHI. Yeah, you put I there.
Okay.
Now let's say you are finding a common ancestor for G and H. Okay. when you are finding G and H at this step number 5, we are checking G on the left side of B. Even I also you are checking on the left side of B. In that situation, you will get false, right? Because G is you did not find G on the left side. You did not find I also on the left side. Are you guys following so far?
Yes.
In
Yes.
that situation, you will get false and false. What it is telling is H is not on the left side. G is not H. Sorry, G and I. You are finding for G and I. G is not on the left side. I is not on the left side of B. That means they reside on the right side. Correct? If both are, you are checking left side. Both are giving false means you need to now this is the right time to navigate to the right side. So on the step number 4, what you did, Karanya, on the step number 4, you navigated left side because you found both the nodes on the left side. Because step number 2 and 3, both step number 2 and 3 giving the true. That means both the nodes are lying on the left side. You are going left side. But if you get false and false, that means both the nodes on the right side. That's the place you need to say node equal to node dot right. Are you guys following?
Yes.
Yes.
This is a tricky logic here. That's it's a hidden true, basically a hidden fact, I would say. So step number 5 and 6, what you are telling is you are, yeah, if step number 2 and 3 and 4, 5 and 6 are same. If both the validations are giving false means since you are checking only on the left side, you got the false and false. That means nodes exist on the right side. That is the situation, you go to the right side. So in this situation, if you find G and I, since G and I are not on the left side of B, you will navigate B dot right. What is B dot right? G. Right? Now you find G and I. Basically, that's where you find the common ancestor. So this is how to find the common ancestor. Is it clear or confusion? I know it is a little tricky, but any questions?
So, for example, if we consider the previous case like common ancestor for A and D,
A and D. Very good. Yeah, A and D. Okay.
in that case, so as we need to check node the root one which is equal to the common ancestor value or not, and
A
if
and
it
D,
is
right?
true, again we need to go for left, right?
A and D, what we do is first we'll assign node equal to root. Step number 1. Right? Let's go with the steps. Okay. Node equal to root, which is node equal to A. Okay.
Yeah.
Now step number 2. Is A on the left subtree? Is A. You are finding A, right?
No.
You will get false, right? Put false because A itself is the root. Now step number 3. Is D on the left subtree of A? Is D
False.
false? Yeah, as I said, you get both the false. Both are false, right? So now what we do is uh, wait. I think there is one condition we need to see.
Yeah.
Let me look at the code. So this you should not go to you should not even navigate to the right in this situation, right? Because A itself
Uh,
is A itself
with
is the
each condition, we'll check whether the how we are finding the H by comparing the exact H with the root which we are navigated to, right, Suresh? So in each
compare.
condition, we will check the root value is the value we are searching for. Then we'll
Yes,
stop
yeah,
there itself.
exactly. That is the condition. We don't want to do step number 2 and 3 also. In this
Yeah.
situation, if you so here FCA in this FCA algorithm, there are three inputs. In the FCA algorithm, you put one more input, that what is the value of root in the FCA before
Okay.
step number 1. Yeah, first you need to put the root, and then
Root.
root is a comma,
Okay.
yeah,
Then.
root, and finding a and d. You are finding common ancestor for a and d.
Then.
Now before you even checking any of these steps, before even step number 1, you will check whether the value of root is equal to either of those nodes. If root equal to node 1 of, let's say, p and q, a and d are the p and q. If root equal to p or root equal to q, then root is the common ancestor. You don't need to check any of these basically.
If root equal to a,
A,
or
or root equal to d.
okay, then we
In
are
this
stopping
situation,
there. Okay.
just return the root because that is common ancestor, right? Here that is the common ancestor for a and d, correct, Vinila?
Yes, yes. So,
You
but
no need
we
to
need
check any.
to,
Yeah.
okay. But we need to, like, whatever the elements that we are taking, that should be in the like in the tree structure, right? So,
Yes,
that,
definitely. So you're asking like whether D is in the tree or not, correct?
yes, yes.
Yeah, that definitely we need to do that validation before even starting the algorithm. That's right. If if D is not covered in the tree, then there is no point. So you're simply written, hey, given input is wrong. Basically, let's say you're asking for a common ancestor for A and K. A and K. K is also an instance of node, but K is not in the tree. So before even starting this algorithm, we need to see whether the nodes you are giving. Let's say I'm giving K and M. I'm giving two nodes, K and M, and root is root. Root equal to A. K and M, is K is covered in the root? Is M covered in the root? No, it's
No.
not there. We simply return false. We don't even check any of the algorithms. So that validation check we need to do, error check basically. Yeah. So once you find those true, that means once you find those nodes, then you will start finding the common ancestor. Okay.
Okay.
So I can show the code and explain. Is if it is everybody is clear on the algorithm. Is it clear, Aravind?
Yeah, Suresh.
Awesome. So should I share this screen and show the code, Karanya?
Yeah, yeah, Suresh, I'll stop sharing.
Yeah. Thank you for explaining. This is good actually. You're writing and explaining everything. Yeah.
Thank you, Karuna.
Oh, thank you.
Now let me share the screen and share my audio as well. Okay. Let me know once you're able to see my screen. Okay.
Yes.
You can see the screen. Right? So here is the algorithm. We had approach 1. So here is the tree I drew here. Um, all the setup code and this one approach 1 we already discussed. We can discuss again later, but since we discussed about approach 2, so I created 3 methods here. It's kind of helper methods. Okay, first one is the common ancestor with the no parent links. As I said, there are 3 input variables. First one is the root, and second one is p and q. Basically p and q are the references. So here we need a reference to root. So in the first algorithm, we don't need reference to the root in the first approach, because you have a parent node. You can just navigate, go back, up, up, up. You can simply go up, and you can find the common ancestor. But here there is no way, since you cannot access the parent. You need to start from the root. Here we need a reference to the root. Now P is the first node and Q is the second node. You need to find, of course, P could be A and D or H. We don't know. So the P is just a reference to any of these nodes. Let's say G and H. So G is P and Q is H. So basically, these are the two reference variables that we need to find the common ancestor. So and there is another, here is the helper method and here is the covers method. I will show you what is that. The first step is error check. This is what Vanilla said. If I give you root and if I am saying m, find m, there is no m here, right? But I can simply create, let's say I can create node m equal to new node, okay, of m, but m is not connected to any, I did not change any of the left or root or anything. So now if I am trying to find common ancestor, this is the method, common ancestor with no parents. Instead of inh, if I say, if I give you the m here, then we need to return null, right? There is no common ancestor between I and m. So that's what the first condition is, error check. No node is, so if the one node is not in the tree, let's say if either of the nodes, either p or q, is not part of the tree, then we simply return null. You don't need to do the any algorithms, you don't need to do any calculations or finding the common ancestor, because the node itself is not part of the tree. So that is the covers method will do. Even we use cover method every time. So cover, what is covers method do is we, it will take two things, root and value you want to find. Okay, so what it does is, it's a recursive method. If root equal to null, return false. There is no way, if the root itself is false, there is no tree. And how can we find p? Simply return false, right? You did not find p. So basically covers will tell you whether you found the node here, the node p is in the root in the tree or not. If you find p in the tree, it will return true. If you did not find p in the root in the tree, it will return false. So if the root is false, if the root is null, there is no tree exist, so simply return false. Otherwise, if root equal to p, that means if both values are same, return true. Okay. So how do you find? Basically, here is recursive method. It covers of root dot left comma p or covers of root dot right comma p. So basically, if I go here, so I'm asking, this is a sub problem. This is not the main problem. So the covers will tell you, this is, let's say, a, root equal to a and h. So you start from here and find h. So find h could be on the left side or right side. How do you know? So what we can do is, we will call the covers method recursively until this is the root and this is the p, right? Until both are same. So first, if I call you the covers method with a and a, what will happen? Both are equal, right? R equal to p, root equal to p. So a is there. But if I call a and h is here, you need to find whether h is on the left side or right side. So you simply call the recursive method here using root dot left and root dot right. So that's what we are doing. Is b equal to h? So you're trying to find h, right? Is b equal to h or c equal to h? Okay, no. Is b dot left, is d equal to h or e equal to h? No. Is h dot left side, nothing here, null. Is e dot right side h? Yes, you found h. That's recursively. Of course, it will give you the false here. You did not find h on the right side, but you found h on the left side. That's what we are doing here. So you are going left side and checking both are equal or not. Again, you are going right side and checking whether both are equal. At some point, because it is a recursive method, it will go on left and right. It will check the value until you find the h. Correct? This is just a finding algorithm. Is it clear or no? It's a recursive, but it is little bit
Yeah.
confusing as
Yes.
basically you are finding a node in the tree. How can you find a node in a tree? There are different ways of doing it. This could be there is one way is basically level by level, which is BFS, right? Breadth first search. So this is basically, I would call breadth first search. Yeah, this is breadth first search only, because you are finding, first you are checking whether the node P equal to root or not. If the root and the node what you find are equal, then return true. If you did not find the root, if you did not find the node, you are checking with left side, is the left of the root is equal to P, or right of the node equal to P. It's a or condition here, right? So since we are putting here, because we know this is a BFS, because root node has only two elements. You no need to put in a queue, or you no need to process. If it is in a queue, you need, if it is a normal tree has many elements, right? Let's say 3 elements. Then you need to put in a queue and then compare. But here, no need, just left and right. Always left and right, always only two elements at the next level. Correct? So that's why we are calling with using left and right. Basically, this is exactly the level wise search. This is level wise search for a node in the tree, which is BFS, breadth first search. Is it clear to everybody? Karanya, is it clear?
Yes, Suresh.
So this algorithm will tell you whether this particular node exists in the tree or not, right? If you find, let's say, if I'm asking you cover A and M, if I say A and M, so if you go either left side or root side, finally you will get null. You will get false, because at some point root becomes null, right? So root is here right now. Root dot left, root dot left, root dot left, and f dot left is null. Similarly, g dot right and g dot right is equal to null. H dot left is null, h dot right is null. Finally, at some point, recursively, root becomes null and you will get false. You never find M in the tree. So this is a recursively we are finding whether this node exists or not. So now what are we doing here? In the first iteration, we want to make sure the given nodes P and Q, if not equal to covers, right? If P is not covered in the root or Q not covered in the root, it's a not condition. If either of these false, that means there is no common ancestor. This is the error checking condition. If this becomes true, and if this becomes true, that means it will come to here. That means both the nodes exist in the tree. Correct? Now we are starting the actual algorithm. Okay, we are sure that P is in the tree, Q also in the tree. Now we need to find the common ancestor. So how do you find common ancestor? Is we just discussed about the algorithm. First condition, if root equal to null, again there is another problem. Sometime, like between these two lines, somebody send root equal to null. Then the problem is, again the root is null. Root null means, there is a root itself. If root equal to null, then that is the common ancestor. You can simply call null. Otherwise, if root equal to P or root equal to Q, this is the condition where we discussed. If either of these nodes is equal to root, then that will be the common ancestor. Correct? So that's what we discussed. Let's say common ancestor. What is the common ancestor for A and C? A itself is common ancestor. So root value is A. This is root. This is P. This is Q. Right? So we are calling with three values. Now root equal to P. In that situation, root itself is common ancestor. That's what we are sending. If root equal to P or root equal to Q, then that's the common ancestor. Otherwise, what are we doing? So this is P is on left side. P is on left. Covers equal to root dot left dot P. So we are finding whether P on the left side of the root. Okay. This is a step number 2 in the steps written by Karanya. Again, next one is Q is on left. We are searching for P on the left side of the root. We are searching for q on the left side of the root. If you find both, okay, if both are not equal, that means, so one is true, other one is false. We don't know what it is. This could be true, this could be false, or this could be false, or this could be true. If both are giving you different values, so nodes are on different side. So one is on the one side, the other one is on the other side. So the root is the first common ancestor. In this situation, if you find like this, right? If both are not having same values, that means that root is the common ancestor. Okay. Otherwise, what happens here? Control comes here if both P and Q are on the left side or both P and Q on the right side. So here control comes here only if both the values are either true or false. Correct? If both the values are same, it could be true. Both are true, or both are false. Now we will check. We will see child side. We need to go if on the left, okay, p is on the left, equal to, let's say this is true, we will go to the left side, otherwise we will go to the right side. So we need to very carefully understand the situation here. We are checking only p. Why are we not checking q? Here see, we did not use a q is on left, we did not use. Why? Are you guys following? Because both have same values. Right? If this condition is failed, control comes here. That means both have either true and true or either false and false. Correct? If both have true, this is true. This is what we are checking. Is P is on the left. Are you following, Vanilla?
Yes, yes, got it. So if all the if whatever the ancestor of D and C both are in the right, again if Q is also false, but we are taking that right part, right, from the line 156.
Exactly. If this is true, that means both are on the left side. Let's go to the left and call the same method. Call the same method using the child side. Child side could be either right or left. If both are true, that means both P and Q exist on the left side. Let's take the root dot left. Okay. If this is false, let's take the root dot right, because both p and q are on the right side. So now you found the child side. It could be right or left. Now you are calling the same method using the child side. This is a little complex to understand, but this is basically exact steps what we laid out, like basically Karanya wrote exact same steps.
So for
Karanya,
example,
are you following? Yeah, go ahead. Yeah.
so for example, if both are different case, like true, one is true and one other one false, then parent is the one which has root. If both are
Exactly.
false,
Yeah, both are false. That means you know this condition, right? This is a simple if and else condition.
yes,
So
ternary
if
operation.
both are false, that means both are false. That means P did not find on left side, Q did not find on right side, left side. P is not there on the left side, Q is not there on the left side. What it is telling is indirectly both are on the right side of the root. Correct? That is the fact. So you did not find P on the left side of the root. You did not find Q on the left side of the root. But you know that P and Q are already in the tree.
Yeah.
That is the fact. We are checking the error condition here. Both P and Q exist in the tree. Okay. But now they are not part of the left side. What it is telling is if they are not part of the left side, they will be on the
Right side.
right side. That is what we are telling. So if you find false here, that means you need to go to the right side. If you find true here, that means you need to go to the left side. because both found on the left side. Got it? Karan, did you follow?
Yes, Suresh.
Yeah, it is little complicated. A single line is defining where you need to go. This single line 156 is very complicated to understand, but that is the actual thing that does the magic here. So this will decide basically that line number 156 will tell you where to go, whether you need to go left side or right side based on the value. Based on the value that will get for this one. Aravind, did you follow this one?
Yeah, Suresh.
Yeah. So this is a recursive function. So
Hmm.
again, what will happen? Yeah, go ahead. Go ahead. You're asking something?
No, I was saying that this could be done using recursion only, I think.
Recording is on.
Okay, I started recording again. So yeah, we cannot use the BFS, but it is kind of BFS only. If you look at here, right? So we are, of course, we are going either only left side or right side. We are not going both the sides based on the values, right? So in this situation, let's say you are finding for I and H. Let's say we want to find first common ancestor for I. I is here and H is here, right? So what happens here? You start with A and you find I and H. Okay. So what will happen? What is the value for P is on left? P equal. This is P, right? This is P and this is Q and this is root. So P is on left. What will happen? P is on left. Are we getting true or false? Because you start with, here is the root. You will find the P on the left subtree of this tree. Did we get true or false? Here is I, right?
Yeah, it is on the left subtree.
Left of A. It is on the left of A. So you will get
Hmm.
true, right?
True, yeah.
Now is Q. Q is on left. Q is on left. Q is H. Here is H.
No,
True or false?
false.
No, you start from root. You started at A. Is H
Okay,
on the
okay, yeah,
left side?
H is on the left. Yeah, yeah. It's,
Exactly.
yeah,
H is also
yeah,
left
yeah.
side. So you will get
Yes,
true. So
yeah,
once you get both the values are true, that means you can safely ignore the right subtree. Here is the right subtree of A. So let me use another color. So you can safely ignore this entire left subtree, right subtree. It could be one node or 100 nodes or 1,000 nodes. Don't care because you found both I and H on the left side. Correct? So if both are true, what will happen according to the algorithm? So that means this is not, both are true. That means we are checking if both are different. This is not equal to, right? Now true and true is equal to true. We should not return root at this point. We are returning root only if the values are different, right? But now both the values are true. If both values are true, control comes here. Now we need to find where to check, where to go. Do you need to go to left side or right side? Now, if the value is true, we need to go to left side because you found P on the left side, you found the Q also on the left side. So now what happens? Child side becomes, now you are calling the same method using B because that's what we go, right? We go to the root dot left. I hope this will make it clear, right?
yeah.
Recursively, we are doing
Hmm.
recursively. We will follow the same approach, but now we will start from the B because we found both on the left side. Did you follow, Vanilla and Karanya? I just want to make sure you understood
Yes,
the
yes,
algorithm here.
Suresh. Yeah.
Both are, now what happens here is, now using B, what will happen? Step number, P is on left. What will happen? So you will find H, you will try to find I, which is P, on the left subtree of B. Is true or false?
True.
True. This will give you true. Now Q is on left. What will happen? You are trying to find H on the left subtree of B. True or false? Tell me.
False.
False.
False. Exactly. Because H is not on the left side. H is on the right side. But we did not check that. We did not check whether H is on the right side. We no need to, because you already did the conditional check before even starting this algorithm. You already know that H is on this tree, and you got the true in the before step. So you checked for H using from A. You already found it. So you are very safe that H is on the right side of B. If so one value is true, another value is false. That means both are not equal. That means this condition satisfied. The condition number, line number 156 is satisfied, right? Nodes are on different side. So root is the first common ancestor. Simply return root. What is the value of root right now?
B.
B. That is the answer, right? If you find what is the FCA, first common ancestor for I and H, is B. B is the answer. You guys followed so far? This is complicated, but if you follow step by step what are we doing here, then you can easily.
Yeah.
Yeah, Karnya, is your child understood?
Sorry.
Yeah,
I
yeah, he
understood.
replied saying, yeah.
He understood B and he replied it.
Yes. I think he can easily, write problems, once he grown up,
Now he's reading himself. I don't know where he learned it.
Nice. See, that's good. So this is the algorithm. This is one of the very common, I think, very important algorithm in interviews, in my opinion, because even when I go to Amazon, I got this problem. So they asked me to write this algorithm. So it's very important to learn. So there are different approaches. There is one more approach. Let's say another problem here. Since we discussed about the algorithm, find out we are doing unnecessary thing here. What is that unnecessary thing? When you start with A, you are finding for I. When you start with B, you are again finding for I.
Yes.
Right? Same thing. When you start with A, you are finding for I and you are finding for H. When you start with B, you are again finding for I and you are trying to find H on the left side. So left side, you are checking and checking and checking and checking. You are always checking. There is unnecessary, some kind of repetition is happening. There is one approach. I did not, in the book there are three approaches. This is the first approach is using parent node, and second approach is this one. There is one more approach where you can optimize this. Even I did not look at the solution, so we need to find. So if you guys have that cracking the coding interview book, find out there are three approaches described there. I need to look at the approach number 3. That will give you optimizer thing, because these nodes are just only 10-15 nodes are okay, but if you think like million nodes, you're always checking, do we have the node on the left side, do we have the node on the left side, do we have the node on the left side, like you are checking that iteration, like you are doing many times. You're starting with another root and you're checking, did you find the root on left side, right? So there is a repetitions going on, a lot of repetitions going here. So that we can eliminate. Okay, so we'll see that problem next week. I need to look at that algorithm, but this is the kind of algorithm. So I need to look for the what is the complexity wise. Even I'm not sure about the complexity. This is a BFS, right? Order of p plus q, or no, log p plus q, I don't know. So it's like, it's not only one time, you're repeating many times, right? I need to find what is the algorithm, what is the complexity of this algorithm. I think it may not be order of n, because you're not checking all the nodes, right? You're not checking on the right side, correct? It definitely not order of n. Oh, maybe order of n, because you're checking at least for the condition, like for the base condition. For error check, you need to check for entire root. If you avoid the error check, what is the algorithm, the
Yeah,
complexity
for
of the algorithm?
covers, we have to check the whole tree, right, Suresh?
Yeah, for the first time, yeah, that's what error check. This error check is covering the entire tree, but actual algorithm, you are not checking the entire tree. You are checking only on the left side, left. Of course, left or right, based on the value you get, right?
Log of
log of uh, log of p plus log of n, I'm not sure. Log means only one time check, but you are checking multiple times.
yes.
So I need to look at the complexity of this algorithm. But yeah, that's a approach number two. But if you guys want to look at the just algorithm for approach number one, this is also a little complicated here, but this is like this is the algorithm we just explained in the beginning, right? So basically what you do is, if you want to find between I and h, we'll we'll start from I and h itself and find the depth of approach one. What we do is, we need to find the depth of I and depth of h, and we will find the differences. So in this case, depth of I is 1 2 3 4 5, and the depth of h is 1 2 3 4. So that's what here. See here, in this first approach, we don't need reference to the root, because you can access parent node, right? So here is the node format. Every node has data, left, right, and parent. So you can easily navigate to the parent. Of course, for the approach number two, I did not use the parent, but for approach number one, we can use the parent. So we don't need root. In this situation, we don't need root. So how are we finding depth of p? Depth of p is, here is the depth function I wrote here. So depth function is basically, you start from here and depth equal to 0. You go all the way to the root, basically parent. Node equal to node dot parent depth plus plus, node equal to node dot parent depth plus plus. Basically, you are navigating to the end of the linked list. You can think of as a linked list as a, parent is the next node kind of thing. It will go all the way to parent, and parent's parent, like root node. Root node's parent is null, right? When you are at the a dot parent equal to null. So that will give you the depth. So you start from I here. Of course, this particular slate is like so many colors here. So now you start with I, and then F 1 2 3 4 5. So that will give the parent of A is null, right? Again, you start with depth of Q. Depth of Q is, let's say you want to find I and H. Now you start with this one. So depth of H is 1 2 3 4. All the way to the parent, right? You navigate to the parent, correct? Are you guys following so far? This is approach number one. So after calculating these two depths, you will find depth of P and depth of Q. Now I'm just printing those depths here, and you are finding the delta. What is the delta? Difference, get the difference in the depths. So once you find the delta, you find what is the first node and what is the second node. If delta is greater, first node is shallower node. This is the node that touches first. So that will give you the first node and second node. Now this is go up, move deeper node up. So second node will give you the deeper node. If delta is greater than 0, then we'll find the p is the deeper node. Okay, in this situation, p is deeper node, because if you do 5 minus 4, 5 minus 4 delta equal to 1, 1 is greater than 0. That means p is deeper, right? Now p is, what is the p here? P is I here. So I is deeper than h. From the root, if you're looking at from the root, I is very deep. So now you need to go up. You need to go up. How many levels? Only delta. Move deeper node up by delta node, so that both are at the same level, right? So go up is basically does the same thing until delta becomes 0. Delta equal to 1 at this point. So just it will go to one parent. If delta is like 5, it will jump 5 times and then both at the same level. Got it? If the tree is really big, okay, I will give you node at level number 10 and another node at level number 15. Level number 10, another node at level number 15. So now you need to go 5 levels, right? The deeper node is at the 15. So you need to go 5 levels. So tree is really, really big. Okay, one node is here, one node is here. This is level number 10 and this is level number 15. So now you go 5 times and you find some node here. Now both are at the same level. Now you will go at the same page and find the common ancestor. Okay, this is the root, let's say, but this is common ancestor, right? Once both are at the same level, you start navigating at the same page. That's what we do here. Go up is done. So now you both are at this. Now move upward from both first and second and find where paths are intersect. Basically, if first not equal, as long as first and second not equal, and first not equal to null and second not equal to null, first equal to first dot parent, second equal to second dot parent. Okay, if any of these null, there is no common ancestor. That means there is no common ancestor. Otherwise, first is the common ancestor. First or second one doesn't matter. At this point, both first and second points to the same intersecting node. And that is the first common ancestor of the given nodes. Okay. So this is the algorithm. I will send you the code. I know it is complicated, but try to see if you can understand by looking at the code. So basically, you will navigate once you are at the same level. This is at the same level. This is at the same level. You navigate the same, like parent, and check is two are same. Is these two are same? And finally, these two are same, right? If you go all the way here, both the nodes intersect here. Both first and second will be same at some point. Then that will be the common ancestor. Is it clear, or is it did I explain really fast?
No, will we get that 109 case?
109. Okay, 109 is in this situation we don't have access to the root, right? Let's say I will give you find common FCA for E and M. E and M. So M is like this. M is here and M parent is K. So here I give you two nodes. I did not give you the root. So E and M. Okay. So now what is the level? So M is not even in the tree, right? There is no way E is here. E is here. This is E and here is M. Okay. So now simply you are finding what is the depth of E. Depth of E is 3.
Yes.
Minus depth of M is 2. Right. So which is delta 1. Now you jump one node and you start from B. You start from B and M. Is B and M same? No. You go to the root of B. A and K. Is A and K are same? No. K's parent is null and A's parent is null. Both are null. That is the situation here. First is null, second is null. Then the situation null. There is no common ancestor. Because you are sending two nodes E and M which are not even in a tree. The one E is in one tree, M is in a different tree.
Yep, got it.
So that's a very good point, because at any point, like you are not checking error checking here. If you look at here, this is directly you are doing this recursive function here. It's not recursive, sorry, this is not a recursive function, but you are directly navigating from P and Q. We don't know what is root here. So we don't know whether P and Q belongs to the same tree or not. That's why we need to check for this condition. If both are not part of the same tree, at some point it will go to the null. So I can run quickly and then we can wrap up the class. And here is the tree, and I'm finding ancestor for I and H. I and H and A and H. These are the three conditions I checked. Here is the exact same situation I did. I created K and J, which is a completely different tree, and you will get FC and null. You are finding to find a common ancestor for D and K. K is in this tree, and D is on the top tree. D is here. So there is no K here, right? So that should give you the null value. Is it still running? That's the problem. It's still building. I don't know why it is building. So that is these are the two approaches. First approach has a conditional thing. We need to have access to the parent for the first approach. So for the first approach, we don't need to access to the root, but we need to have access to the parent. And second approach is we don't need access to the parent, but we need access to the root, and we are doing a lot of iterations here. That is the problem of this second approach. So that we can eliminate. Let's see if there is approach 3, we'll try to eliminate. Now look at the tree here. Okay, first common ancestor of the tree here, I and H, the depth of I is 5, right, and depth of H is 4. So that's why now the first common ancestor for I and H is B, right? So I will jump only one time, and then it will start from G. G and H are same? No. D and E are same? No. B and B are same? Yes. So first and second, there are 2 pointers we are taking in the algorithm. First represents this one, second represents this one. So we'll go up, right? That's what in the approach 1. That's what we are doing here, right? So second and first. If both first and second are equal, then that's a common ancestor. So that's the approach that we followed. Now common ancestor for I and H. This is the approach number 2. Even on the approach number 2, you got the same answer. Now first common ancestor for A and H. A and H. A is here and H is here. So that will give you the A's answer. Now there is no common ancestor for D and K. They are from 2 different trees. So I passed D here. Here is the D. Here is a D and K. K is a different node altogether, and K's parent is J. Basically, J is the root of different tree, and K is the first node. So now I am saying, is there any common ancestor for D and K? D is on this node, so there will be a different. I would say something like this. J is here. J is here, and J dot left equal to K. Is it left or right? Yeah, parent. J dot left equal to K. So now I'm trying to find, is there any common ancestor for K and D? There is no way, right? K is in a different tree. This is in a different tree. So that's why we'll say null value here. If I get the null value, I'm printing there is no common ancestor for these 2 nodes. I'm just printing that particular value. Okay, this is tree number 2, and this is tree number 1. Is it clear, or any questions? It is complicated, but great. So far, so good. Thank you for following so far. So we are almost ending up the trees concept. So maybe I will see if we can find the third approach. It is a little complicated. I will check that. Once we complete that, probably we'll jump into the graphs. So really another great interesting concept. I still need to list out all the problems here. There are a lot of problems. At least I can explain at least 5 to 6 problems on the graphs. So stay tuned and please join so that you will get more idea. Like I'm giving these sessions for your, I think it will definitely help your interviews. Okay, so I hope this time is okay, or from next week anyway our times are changing. I'm okay to change any times. Let me know if any problem of joining this time.
That's fine.
Okay, Karni, is it okay for you? Are you already settled with this time, right?
Yeah, I'm settled for this time.
Yeah. Or maybe if you want, we can also move a little bit around. So let me
No,
know.
let others decide, Suresh. I can manage in the weekends because my husband is at home.
So any time is fine with you.
Yeah, in weekends, any time is fine with me. I'll manage.
Yeah, let's see. I will check. If we need, we will change a half an hour here or there. But if this time is okay, we'll continue the same time. Arvind, is it also okay for you, right?
Yeah, Suresh, this is fine.
Awesome. So, and are you preparing for interviews? Did you schedule? You said you got some interviews
Yeah,
coming,
yeah,
right?
no. I actually had some personal problems, so I had to like postpone the interview.
Oh, I see. I see. Okay, okay. Yeah, you still get some prepare when you get some time.
Yeah,
Prepare
yeah,
all these arguments.
sure.
Yeah. So next week I will cover the approach number 3 for this common ancestor, and then we'll jump into the graphs problems. And then there are a lot of other topics. Is sorting algorithms. As there are 10 types of sortings that I practiced before. So I will explain that as well. I think yeah, that's it pretty much. Awesome. Thank you, everyone. I think we had good session
Thank you,
today. I
Suresh.
hope.
Yes, thank you
Yeah.
so much,
Yeah,
Suresh.
we had a good section today.
Awesome.
Thank you,
Awesome.
Suresh. Thank you all.
Thank you,
Great.
Arvind. Thank
Okay.
you, Arvind.
Have a nice weekend, and see you next week. Okay.
Bye. Bye.
Bye bye.
Bye.
Bye.